Okay, this is the final part of this May 2024 Edexcel Physics International A-Level, which is for Unit 4, which covers further mechanics, field theory, and particle physics. So we've gone through all the questions apart from question 18, the final question. And just to give you a heads up, if you find these videos useful, don't forget to like, share it with your friends so we increase the number of subscribers. Aim is to get 1,000 subscribers as soon as possible during this academic year. We're up to 720 nearly, so we're well on our way, 70% there. And just wanted to let you know that the mark scheme for October 24 is now available. So if I get a chance, I will be uploading that before your Unit 4 exam if you're taking this exam in January. So watch this space, make sure you're subscribed so you get notified. This will probably be the last video for A-Level of 2024. So thanks for supporting the channel if you've been watching it for a while, and if you're new to the channel, hope you find it useful. If you look in the playlist, you'll find there are plenty of videos on Unit 1, Unit 2, a few on Unit 3, not that many. There's some on Unit 3, Unit 4, which was this one, Unit 5 already, and a few on Unit 6. So the main focus for January for my students is Unit 1 and Unit 4, although I have started to put some linear exams as well, which Paper 1 is very similar to Unit 4. Okay, so without further ado, let's get into question 18, just about magnetic induction, electromagnetic induction. It says in some car engines, well in most car engines, petrol engines, the power is provided by burning a mixture of fuel and air, and the photograph shows a spark plug, and that spark from the spark plug ignites the fuel, okay, the fuel-air mixture. The spark plug creates a spark that ignites the mixture. A very high potential difference, PD, across the gap shown by my arrow, where the gap is, in the spark plug is needed to produce the spark. So we need a high voltage. So they're saying this very high potential difference is produced using the arrangement shown. Now you have a primary coil and a secondary coil on an iron core. Now, you know why it should be an iron core. So in the GCSE question I looked at recently in paper 2 of GCSE Edexcel, they ask you these questions, what is a transformer? Well, this is effectively a transformer where you've got the primary coil and the secondary coil around an iron core, and they say, well, we know, how does a transformer work? What is the transformer theory? And obviously the secondary coil is where we want to have the high voltage. So presumably the secondary coil will have a larger number of turns than the primary coil to create that high voltage that we want with a high potential difference. So we need to understand transformer theory. But in this case, they're using a 12-volt battery. Apologies, I'm pressing the wrong thing. I want to get my pen. So here you see they're using a 12-volt battery. That means they're using a DC. So when you start your engine, this is basically the starter engine. You have access to the 12-volt battery, which suddenly switches on in the primary coil, and that sudden switching on of the primary coil induces a magnetic field in the iron core. Yeah, so I'm assuming that this will be an iron core. I can't imagine what else it will be. And that then induces a magnetic field in the secondary coil. And because the secondary coil has a much larger number of turns compared to the primary coil, yes, then you'll get a much greater voltage output, okay, across this gap, okay? So when you switch on your car, that's what the switch does. It connects you to a 12-volt battery. That induces a sudden change in the magnetic current, a sudden change in the magnetic field, and that's what causes the spark. Okay. So it's now describing what I've described to you. It says the switch is closed and the current in the primary coil increases from zero, basically. Current increases to a maximum value. The switch is open. The switch is then opened and the current falls to 0. Yeah, almost immediately. So the time, they're saying, the time for this to happen almost immediately is approximately 0. The secondary coil produces large PD by electromagnetic induction, which is due to Faraday's law. Yeah? And this creates an electric field strong enough to cause a spark across the gap. So this is their introduction, and I hope you found mine useful as well. And it says explain. So explain means don't have to just say it, you have to say why does it happen, how a PD is produced, yeah, across the secondary coil when the switch is opened. Okay, so the switch is first closed. When the switch is first closed, the current in the primary coil will create a magnetic field, yeah, and is increased substantially by having an iron core, yeah, because an iron core is a soft magnetic material, so it's easy to magnetize, yeah, and that's when the switch is closed. So this is the initial bit where the current produces a magnetic field, and then when the switch is opened, the current changes to 0, so there is a change in the magnetic flux. So sudden decrease in the magnetic flux. This change in flux linkage in the secondary coil is what induces a magnetic field, or induces an EMF, across the secondary coil. And I've put, well, this is Faraday's law. Okay? So that's how we're going to get, hopefully, those 3 marks. Okay, I'm just going to rub out this line that I drew accidentally. Anyway, I hope that makes sense to you. The distance across the gaps, across the gap in the spark plug is given to you. Yeah, so D is given in millimeters. So don't forget, you've got to change that into SI units. And then it wants you to calculate the electric field strength in the gap. Yeah? And to get an electric field strength in the gap, yeah, you have a uniform electric field there because it's basically a voltage across a distance. Okay, so you can assume the electric field in the gap is uniform. Okay? All right. And then they're giving you data to that you need to use. They're giving you the flux density in Teslas, so that's B. They're giving you the number of turns in the secondary coil, that's N. Yeah. Let's just try and do that a bit more neatly to change the color. So N is given to us as 30,000. Sorry, it's a bit of slanted angle. And then the diameter of the secondary coil is 16 millimeters. So why do we need that? Well, we need the diameter to be able to work out the area. Yeah? And if you do that, you will see that you can, once you've got the area, you'll see this green box here. Is how you get the cross-sectional area or the area of the coil, because that's for flux linkage. And then the time it takes for the current to fall to 0, yeah? The time it takes for the current to fall to 0 is given to you here. So we know B, we know A, we know, well, we can work out A, I should say. So A is pi r squared, yes, but they're given it as diameter. So you need to change that to R. Yeah? So I'm just going to have a look at the mark scheme just to make sure I haven't made a mistake in my calculation. Yeah, so this is 16 times 10 to the minus 3. That should be 8 times 10 to the minus 3. Yeah, because obviously you need to divide that by 2 and then square it. So 8 times 10 to the minus 3, or d over 2 all squared. Anyway, that does give you, this is the correct area. So I just forgot to divide it by 2 and to 2 significant figures. See, all the data provided is to 2 significant figures. And once you know that, you can then work out the EMF. Because the EMF is the magnetic field times the area, which is the flux. Yeah. The rate of change of flux is then divided by T, yes, by multiplying by N, because that's N d phi by dt if you think of it as a calculus term. Okay. So once you put B in there, A in there, which we calculated, and N in there, and divide it by the small time it takes, this gives you the answer of 1.0 times 10 to the 5 volts to 2 significant figures, and that is the voltage that's been induced. Okay? So once you've done that, you can, what do they want us to do? Calculate the field strength. Well, we know that the field strength is V over D. So that's worked out here. E is V over D. And then you put the numbers in. V from above. D was given to us as 75 millimeters. So that's 75 times 10 to the minus 3. And you'll get volts per meter to 3 significant figures of 1.37. Okay, times 10 to the 8. And once you've done that, you need to round it up because all the data is given to 2 significant figures. Yeah. And once you do that, it will come to 1.4 times 10 to the 8 volts per meter. Okay, so we have determined the electric field strength. So here I was just showing you that when we did BAN, BA is also phi, which is the flux, which is the area that's linking with the magnetic field. And that's, I think you can get a mark for doing this calculation separately first, okay, on the mark scheme. Hope that makes sense. Then it says when the switch in the circuit is closed, yeah, the current increases to a maximum value, but there's a delay, yeah. You can see that there's a delay, it doesn't reach the maximum value immediately, yeah. So explain why the current does not increase to its maximum value instantaneously. Well, that's due to the reactance of the coil. The coil is reacting to the change that is trying to create a magnetic field inside of it. So you should refer to Lenz's law, okay? So the EMF induced will act to oppose the change causing it, okay? The change causing it. Now that's Lenz's law, okay? In other words, the EMF induced in the coil will oppose the EMF of the battery initially, okay? So it's a delay that is caused by the magnetic field that's produced inside the coil. And that's called reactance in circuit physics, which is not in this course. This will delay, okay, so the final mark for this exam is this will delay the increase in current until the rate of change of current drops to 0, okay? Because it's only opposed to changes. Once it stops changing, it no longer opposes it, and eventually the current will reach the value due to the resistance of the circuit. Hope that makes sense. Well, that's the end. It took me quite a few days to get it through all of this because it was during the Christmas period. I hope you found it useful. And that's probably the last unit for 2024, as today is December 30th. But I will try to do the October 2024 exam if I get a chance, and that might be next week. Okay, so good luck in your revision. If you have any comments or questions, feel free to ask in the relevant video, and don't forget to go to the playlist to see if you've watched all the other papers that were previously uploaded for whichever units you're looking for. So if you go to the channel, you will find a place on the channel where it's got all the playlists, and if you go to the home page of the channel and look at the playlists, you will see that they're organized by the unit of the A level and by the paper number and by the year. Okay, so hopefully you can find quite a few that will help you in your preparation. Anyway, thanks for watching and supporting the channel, and have a good New Year break, and I'll see you on the other side. Thanks for watching. Bye for now.